Hey guys, this is Alan, back to talk a little bit more about p-n junctions, specifically how you can bias the p-n junction to create current flow, which is the fundamental concept of how a diode works. So let's talk about this idea of bias. In a p-n junction, we said earlier that when the p-type and n-type materials are put together, the majority charge carriers from each side of the junction diffuse across the junction, and they eventually come to a point where they're finished diffusing. They've reached equilibrium, and across the junction there is now there's an electric field and there is a voltage potential, and the current at that point is not flowing at all, because they've reached equilibrium. So to get current to flow, we've got to introduce some external voltage to upset, if you will, the dynamic that is currently settled condition inside of the p-n junction. And that's what bias is. Let's talk first about forward bias, which is what you'll use to make the current flow in the p-n junction. Forward bias is achieved by connecting a positive voltage to the P side of the junction and a negative voltage to the N side of the junction. So when you connect this positive voltage to the P side of the junction, there are actually electrons that had diffused, they already had diffused from the N side of the junction to the P side of the junction, and they'd pretty much settled where they were, and they'd stopped moving around. At least, the net movement had stopped. But when you introduce this positive voltage to that P side, the free electrons that had traveled into that P side now will be drawn even further through the P side. They're going to keep going now because they've got extra incentive. That's what this external voltage that's applied has created. It's like an incentive for those electrons to keep traveling through that P side. And on the other side of the junction, on the inside of the junction, we've applied a negative voltage, and what that does is it introduces more electrons back into that side, which draws even more of the holes that had previously diffused from the P side. It pulls them even further through in that direction. And so the result is a net current, and so it looks kind of like this. You've got here's the symbol for this is for a diode, all right? And when we apply this forward bias, what we've done is we've connected the positive charge here and the negative charge on this side of the p-n junction. Again, to be clear, this symbol right here is for a diode, not for a p-n junction. But the p-n junction is what makes the diode do what it does. It is the fundamental principle of why the diode works. So just imagine that p-n junction inside of there, and imagine that we have connected this plus and minus to the actual terminals of the junction. All right? And then when that happens, just as you would expect in typical circuit schematics, current will run from a higher voltage potential to a lower voltage potential. So you get current traveling in that direction. Now we can also introduce a reverse bias. And a reverse bias means that we're switching these. Instead of a positive on the left side and a negative on the right, we're putting the negative terminal on the left side and the positive on the right. And then what happens is when the current tries to flow, it gets blocked. And the symbol for the diode is helpful in imagining this. Imagine the current trying to go this way, and then it just hits this wall, if you will. And that's an easy way to remember that the current can't go backwards. So again, to summarize, under forward bias, current will flow through the junction and through the diode. Under reverse bias, it will not. All right, now I haven't mentioned this before now, but we should take note of the fact that what I've just described applies to an ideal diode. In reality, there actually is a small amount of current that will flow even under reverse bias, and we call that the saturation current. We call it the saturation current because it will not continue to increase. It gets to a certain level, and for a pretty significant range of negative voltages or reverse bias voltages applied, it will stay pretty steady at a particular level until it reaches a Zener voltage, which will be covered further in another video. Let's go forward now into the idea of how we can calculate the current that's flowing through the diode. And to do that, we're going to look at Shockley's equation. And it says here that we can use this to calculate the current through the diode in either direction. That means if it's forward bias or reverse bias. It works for all voltages except those in the breakdown region. And that breakdown region refers to the Zener breakdown region, which again we will cover further in another video. So here's our equation. It's the current through the diode equals I sub S, that's your saturation current that we just talked about, multiplied by e to the V over NV minus 1, where V is the voltage. It's actually usually going to be shown as V sub D, so it's the voltage across the diode. N is the emission coefficient or quality factor, which is usually 1 or 2, and it'll be given in any problem that you have. And the uppercase V, which will usually be shown as V sub T, is equal to KT over Q, which we saw in a previous equation, but in the previous equation we went ahead and subbed in all the values for KT over Q. KT over Q at room temperature, so at 300 Kelvin, is going to equal about 26 millivolts or 0.0259 volts. So that's a figure that if things are at room temperature, you can probably work through your equations a lot faster if you just remember that that's equal to about 26 millivolts. But if the temperature in the problem is not 300 Kelvin, then you can't make that assumption, and you're going to have to actually substitute that temperature in for the T. Let's look at an example now, and let's actually calculate the current going through the diode. A current of 1.41 times 10 to the negative 9 amps, so that's 1.41 nanoamps, passes through a silicon diode when a forward bias of 0.15 volts is applied. If the thermal voltage is 25 millivolts, what is the approximate saturation current? I don't know, guys, if I mentioned that the thermal voltage is from that previous slide. If we go back one slide, that VT, that is the thermal voltage. Oh, we did mention it. Sorry, just want to make sure we had that base covered. All right. So it says if the thermal voltage is 25 millivolts, we said it was about 26 more accurately, but we'll go with 25 because that's what the problem gave us. What is the approximate saturation current? All right, let's work it out. So going to our whiteboard, we will use, all right, we've got our expression that says current through the diode equals the saturation current multiplied by E to the VD. That is bad. Bear with me, we'll get there. V sub T, that's the voltage through the diode, over, and we had NV, and we said that N is the emission coefficient or quality factor, which will usually be 1 or 2, and it should be given. We're going to assume it's 1 if it's not given here. All right, so we're not even going to write the 1. And the V here is VT, which we're given, but we won't substitute anything in yet, minus 1. And we need, the problem says we're looking for the saturation current. So we can say that, working through this algebraically, we can say that IS, that's the saturation current, equals current through the diode divided by E to the VD. That's terrible. I don't talk like that. That's a Charles Barkley impression. VD over VT minus 1. And then we can just substitute in all the missing values because we have our current through the diode. It's given. We know that our VD is given. That was our 0.15 volts. Our VT is given as 25 millivolts. And so let's get to plugging. So we get 1.41 times 10 to the negative 9 amps over e to the 0.15 over that. I'm gonna take our 25 millivolts here and make it volts because the 0.15 is in volts. So I'm gonna go 0.025 volts minus 1. And then when we plug that into our handy dandy calculators, we will get